Welcome to the Whispering Galaxy, where the cosmos whispers its secrets just for you. Tonight, we drift into the deep abyss of our galaxy, a place where physics becomes poetry, and the laws of nature hum gentle lullabies across the void. I wonder, dear listener, where are you joining us from this evening? Perhaps you're nestled beneath warm blankets in a cozy bedroom. Or maybe you're listening while starlight filters through your window. Wherever you find yourself, I hope you're comfortable and ready to let your mind wander through the infinite corridors of space and time. Before we begin our journey into this celestial symphony, I'd be grateful if you could give this video a gentle like and perhaps subscribe to join our peaceful community of curious dreamers. Your support helps these whispered tales of science reach other restless minds seeking wonder in the darkness. Now, settle back and breathe slowly. Tonight's adventure might be so captivating that it keeps you awake with fascination. But if it does, at least you'll drift into tomorrow with your head full of cosmic marvels. So let us begin, shall we, with a question that will guide us through the first constellation of facts. What would happen if we could hear the universe singing? And what stories would the stars tell us about the hidden mechanics of existence itself? In the Whispering Galaxy, every star pulses with the rhythm of nuclear fusion, each one a cosmic furnace where hydrogen atoms dance together in temperatures reaching 15 million degrees Celsius. These stellar hearts beat with a process so elegant it seems almost musical. 4 hydrogen nuclei embrace in a sequence of steps, transforming themselves into one helium nucleus while releasing tremendous energy. The mathematics are beautiful in their simplicity. Each fusion reaction converts a tiny fraction of mass into energy, following Einstein's famous equation that links mass and energy as dance partners in the cosmic waltz. The proton-proton chain reaction begins when 2 hydrogen nuclei overcome their natural repulsion through quantum tunneling, that ghostly phenomenon where particles slip through barriers they shouldn't classically be able to cross. One proton transforms into a neutron through beta plus decay, creating a deuterium nucleus, a positron, and a neutrino that immediately begins its journey through space at nearly the speed of light. This neutrino, so ethereal it could pass through a light year of lead without stopping, carries news of the fusion deep in stellar cores to detectors buried beneath mountains on distant worlds. The deuterium nucleus then encounters another proton, forming helium-3 and releasing a gamma-ray photon that begins an epic journey toward the stellar surface. This photon will spend thousands of years bouncing randomly through the dense stellar interior, absorbed and re-emitted countless times, before finally escaping to illuminate the cosmos. Meanwhile, 2 helium-3 nuclei eventually collide, creating helium-4 and returning 2 protons to continue the cycle, like dancers exchanging partners in an endless cosmic ballroom. But fusion is just the beginning of stellar storytelling. The relationship between a star's mass and its luminosity follows a power law so precise it seems the universe was designed by a mathematician with an aesthetic sense. Double a star's mass, and its brightness increases not by 2, but by roughly 8 to 16 times. This means massive stars burn their nuclear fuel with reckless abandon, living fast and brilliant lives measured in millions rather than billions of years. Our own sun converts approximately 4 million tons of mass into pure energy every second. Yet this represents such a tiny fraction of its total mass that it can maintain this rate for 10 billion years. The energy production is so steady that variations of just 1% would dramatically alter conditions on planets orbiting in the habitable zone, that Goldilocks region where liquid water can exist on rocky surfaces. In the cooler outer layers of stars, convection creates cells of rising hot gas and sinking cool gas, patterns visible as granulation on the solar surface. These convective cells, some as large as continents, transport energy from the interior to space through a process as fundamental as boiling water in a pot, yet scaled up to cosmic proportions. The magnetic fields threading through this turbulent plasma create the complex phenomena we observe as sunspots, solar flares, and coronal mass ejections. When massive stars exhaust their hydrogen fuel, they begin fusing heavier elements in their cores. Helium burns to carbon and oxygen. Carbon fuses to create neon and magnesium. The stellar interior develops an onion-like structure with different fusion processes occurring in concentric shells, each burning at increasingly higher temperatures and pressures. This process continues through silicon burning until iron 56 forms in the core, the most stable nucleus in the periodic table. Iron represents the end of the fusion road. No energy can be gained by fusing iron into heavier elements, so when the stellar core becomes primarily iron, fusion stops. Without the outward pressure of fusion energy to balance gravitational collapse, the core implodes in less than a second. Electrons and protons are crushed together to form neutrons, releasing a tremendous burst of neutrinos that carry away most of the explosion's energy. The core collapse creates a shock wave that propagates outward through the star's layers, but this shock wave stalls when it encounters the dense outer core material. However, the intense neutrino flux, normally ghostly and non-interacting, becomes so dense that even these elusive particles deposit enough energy to revive the shock wave and drive it to the stellar surface. The result is a core collapse supernova, one of the most energetic events in the universe. These stellar explosions forge elements heavier than iron through rapid neutron capture processes. In the extreme conditions of the supernova, atomic nuclei are bombarded with neutrons faster than they can decay, climbing up the periodic table to create gold, platinum, uranium, and other heavy elements. The gold in your jewelry and the uranium in nuclear reactors were literally forged in the death throes of massive stars billions of years ago. The remnant left behind after the explosion depends on the original star's mass. Stars between roughly 8 and 25 solar masses leave behind neutron stars, objects so dense that a teaspoon of neutron star material would weigh as much as a small car weigh as much as Mount Everest. These city-sized objects pack more mass than our sun into a sphere only 20 kilometers across, creating gravitational fields so intense that the escape velocity approaches half the speed of light. Neutron stars spin rapidly, sometimes hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. When their magnetic poles are misaligned with their rotation axis, they emit beams of radiation that sweep across space like cosmic lighthouses. These pulses arrive at Earth with clockwork precision, making pulsars among the most accurate timekeepers in the universe. Some neutron stars exist in binary systems where they slowly spiral toward each other, losing energy to gravitational waves that ripple through space-time itself. When these neutron stars finally merge, they create a brief burst of gravitational radiation detectable by instruments on Earth, followed by a kilonova explosion that produces even more heavy elements through rapid neutron capture. The most massive stars, those exceeding roughly 25 solar masses, collapse so completely that not even neutron degeneracy pressure can halt the implosion. The stellar core shrinks to a mathematical point called a singularity, surrounded by an event horizon from which nothing, not even light, can escape. These black holes warp space-time so severely that time itself slows down near their boundaries, creating regions where the normal rules of physics break down. Yet even black holes are not eternal. Stephen Hawking showed that they slowly evaporate through quantum effects at their event horizons, radiating energy in a process that becomes more rapid as the black hole shrinks. The temperature of this Hawking radiation is inversely proportional to the black hole's mass, meaning stellar mass black holes are actually colder than the cosmic microwave background, and will take longer than the current age of the universe to evaporate significantly. In the spaces between stars, the interstellar medium contains roughly 1 atom per cubic centimeter, creating a vacuum far better than anything achievable in terrestrial laboratories. Yet this tenuous gas is stirred by stellar winds, supernova shockwaves, and magnetic fields that thread through the galaxy like invisible highways. Giant molecular clouds, cool regions where hydrogen molecules can form and survive, serve as stellar nurseries where gravitational collapse triggers the birth of new stars. The cycle continues endlessly. Stars form from gas enriched by previous generations of stellar death, burn their nuclear fuel according to the fundamental laws of physics, and return their processed material to space through stellar winds and explosive endings. Each generation of stars contains a higher fraction of heavy elements, gradually transforming the chemical composition of galaxies over cosmic time. This stellar alchemy has profound implications for planetary formation and the emergence of life. Rocky planets can only form in regions where sufficient quantities of silicon, iron, magnesium, and other heavy elements exist. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones were all forged in stellar cores and dispersed through space by stellar death, connecting every living thing to the nuclear furnaces that power the cosmos. The whispering galaxy holds secrets that extend far beyond individual stars, weaving together cosmic phenomena that operate on scales both intimate and vast. As we drift deeper into this celestial realm, let us explore how the fundamental forces shape the architecture of space itself, creating the invisible scaffolding upon which all cosmic drama unfolds. Gravity, that most familiar yet mysterious of forces, reveals its true nature only when we venture beyond earthly confines. Near the surface of our planet, gravitational acceleration remains remarkably constant at 9.8 meters per second squared. But this apparent uniformity masks a force that weakens with the square of distance. Double your height above Earth's surface, and gravity's pull becomes 1/4 as strong. This inverse square relationship governs everything from the orbital mechanics of satellites to the tidal forces that sculpt planetary surfaces. The concept of gravitational potential energy becomes beautifully evident when we consider objects in orbit. A spacecraft circling Earth at 400 kilometers altitude possesses enormous potential energy relative to the planetary surface. This stored energy can be converted to kinetic energy during re-entry, explaining why spacecraft glow white-hot as they descend through the atmosphere. The friction with air molecules transforms orbital velocity into thermal energy at temperatures exceeding those found in stellar cores. Einstein's revolutionary insight transformed our understanding of gravity from a force into a curvature of space-time itself. Massive objects create depressions in the fabric of reality, much like heavy balls creating dips in a stretched rubber sheet. Smaller objects moving through this curved space follow geodesics, paths that appear straight in four-dimensional space-time, but curve through our three-dimensional perception. This geometric interpretation of gravity explains phenomena that Newton's laws could not address, such as the precession of Mercury's orbit and the bending of light around massive objects. Gravitational time dilation emerges as one of relativity's most counterintuitive predictions. Time flows more slowly in stronger gravitational fields, an effect measurable even at Earth's surface. Clocks at sea level run slightly slower than identical clocks atop mountains, and this difference, though measured in nanoseconds per day, requires correction in global positioning system satellites to maintain accuracy. Without accounting for both gravitational and velocity-induced time dilation, GPS navigation would accumulate errors of several kilometers within hours. Black holes represent gravity's ultimate expression, regions where space-time curvature becomes so extreme that the normal rules of physics break down. The event horizon, that spherical boundary from which no escape is possible, exists at a radius determined solely by the black hole's mass. For a black hole with our Sun's mass, this Schwarzschild radius would measure approximately 3 kilometers, while supermassive black holes in galactic centers might have event horizons larger than our solar system. The physics near black holes reveals the deep connection between gravity and thermodynamics. Black holes possess temperature and entropy, with the entropy proportional to the area of the event horizon, rather than the enclosed volume. This relationship suggests that information in our three-dimensional universe might be encoded on two-dimensional surfaces, a concept known as the holographic principle that has profound implications for our understanding of reality itself. Electromagnetic forces, though much stronger than gravity on small scales, shape cosmic structures through their ability to accelerate charged particles to tremendous energies. Magnetic fields threading through interstellar space guide the motion of cosmic rays, high-energy particles that travel at nearly the speed of light. These cosmic messengers carry information about distant supernovae, black hole accretion disks, and other extreme environments where matter reaches temperatures of billions of degrees. The electromagnetic spectrum extends far beyond visible light, encompassing radio waves with wavelengths measured in kilometers down to gamma rays with wavelengths smaller than atomic nuclei. Each band of this spectrum reveals different aspects of cosmic phenomena. Radio telescopes detect the synchrotron radiation emitted by electrons spiraling through magnetic fields. Infrared observations reveal the heat signatures of star-forming regions obscured by dust. X-ray telescopes peer into the accretion disks surrounding black holes where matter reaches temperatures hot enough to emit high-energy photons. Light itself carries momentum, a fact that becomes important on cosmic scales despite photons having no mass. Solar radiation pressure shapes the tails of comets, always pointing them away from the sun, regardless of the comet's direction of motion. This same radiation pressure could potentially propel lightweight spacecraft using solar sails, gossamer sheets that catch photons like wind in a sailing ship's canvas. The speed of light in vacuum, exactly 299,792,458 meters per second, serves as the universe's ultimate speed limit. This constraint has profound consequences for cosmic communication and causality. Signals from the nearest star system require over 4 years to reach Earth, while light from distant galaxies may have traveled for billions of years before entering our telescopes. We observe the universe not as it is, but as it was, creating a natural time machine that allows us to study cosmic history. When light travels through different media, it slows down according to the material's refractive index. This change in speed causes refraction, the bending of light rays that creates mirages on hot pavement and enables lenses to focus starlight into telescopic images. Atmospheric refraction allows us to see the sun for several minutes after it has actually set below the horizon, as Earth's atmosphere bends the solar rays around the planet's curvature. The wave nature of light becomes apparent through interference and diffraction phenomena. When light waves from two sources combine, they can reinforce each other to create bright regions or cancel each other to produce darkness. This interference principle underlies many astronomical techniques, including the operation of radio telescope arrays that combine signals from multiple dishes to achieve the resolving power of a single telescope spanning continents. Polarization adds another dimension to electromagnetic radiation, describing the orientation of the electric field as light waves propagate through space. Reflected sunlight becomes partially polarized, a property that some animals use for navigation. In astronomical contexts, polarized light reveals information about magnetic fields in stellar atmospheres, interstellar dust grains, and the cosmic microwave background radiation that fills all of space. The quantum nature of light manifests in the photoelectric effect, where individual photons knock electrons from metal surfaces with energies determined by the light's frequency rather than its intensity. This phenomenon, for which Einstein received the Nobel Prize, demonstrates that electromagnetic radiation comes in discrete packets called photons, each carrying energy proportional to its frequency according to Planck's constant. Atomic spectra arise from the quantum mechanical structure of electrons orbiting atomic nuclei, Each element produces a unique fingerprint of spectral lines corresponding to electron transitions between energy levels. Astronomers use these spectral signatures to determine the chemical composition of distant stars and galaxies, revealing that the same elements found on Earth exist throughout the observable universe. The Doppler effect shifts the frequency of light from moving sources, causing approaching objects to appear bluer and receding objects to appear redder. This phenomenon allows astronomers to measure stellar velocities, detect exoplanets through their gravitational influence on host stars, and map the rotation of galaxies. The cosmological redshift of distant galaxies provided the first evidence for the expansion of the universe itself. Magnetic fields permeate cosmic space, generated by the motion of electrically conducting fluids in stellar interiors, planetary cores, and accretion disks. These fields can store enormous amounts of energy and channel charged particles into narrow beams that extend for thousands of light years. The interaction between magnetic fields and plasma creates complex phenomena, including solar flares, auroral displays, and the jets of material ejected from active galactic nuclei. The fundamental forces that govern these phenomena operate according to symmetries that reflect deep mathematical principles underlying physical law. Conservation of energy emerges from the symmetry of physical laws under time translation, while conservation of momentum arises from spatial translation symmetry. These conservation laws constrain all physical processes, from the collision of subatomic particles to the evolution of galactic clusters. As we contemplate these cosmic forces and their manifestations, we begin to perceive the Whispering Galaxy, not as a collection of separate objects, but as an interconnected web of matter, energy, and space-time itself. Every photon of starlight, every gravitational wave, every charged particle streaming through interstellar space contributes to a cosmic symphony of physics playing out on scales that span from quantum mechanics to general relativity. The strong nuclear force operates through a mechanism so elegant it borders on poetry. Quarks, the fundamental constituents of protons and neutrons, are bound together by particles called gluons in a dance of confinement that defies our everyday understanding of forces. Unlike gravity or electromagnetism, which weaken with distance, the strong force actually grows stronger as quarks are pulled apart, like a rubber band that stretches but refuses to break. Within the nucleus of every atom, protons and neutrons nestle together despite the electromagnetic repulsion that should tear them apart. The strong force overcomes this electrical antagonism at distances smaller than the width of a proton, creating the binding energy that holds atomic nuclei intact. This nuclear binding energy reaches its peak at iron 56, which is why lighter elements release energy when they fuse together, while heavier elements release energy when they split apart. The weak nuclear force, though feeble compared to its strong counterpart, governs the delicate transformations that allow stars to shine and elements to transmute. Beta decay, where neutrons transform into protons or vice versa, occurs through the exchange of W and Z bosons, particles so massive they can only exist for the briefest moments before decaying into other forms. These fleeting messengers enable the sun to convert hydrogen into helium, powering the nuclear furnace that has warmed our world for billions of years. Quantum mechanics reveals that even empty space itself seethes with activity. Virtual particles pop into existence and annihilate in timeframes so brief they cannot be directly observed, yet their effects ripple through the universe in measurable ways. The Casimir effect demonstrates this quantum foam by showing that two metal plates placed extremely close together in vacuum experience a slight attractive force, as if the space between them contains less energy than the surrounding void. The uncertainty principle, discovered by Werner Heisenberg, places fundamental limits on what can be simultaneously known about quantum systems. The more precisely we determine a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of our measuring instruments, but a feature woven into the fabric of reality itself. Particles exist in clouds of probability until observation forces them to choose specific values for their properties. Quantum tunneling allows particles to pass through energy barriers they should not classically be able to cross, like a ball rolling through a hill rather than over it. This ghostly phenomenon enables the nuclear fusion reactions in stellar cores, where protons overcome their electrical repulsion through quantum mechanical probability rather than brute force. Without tunneling, stars would never ignite, and the universe would remain cold and lifeless. The concept of wave-particle duality reveals that light and matter exhibit both wave-like and particle-like properties, depending on how we observe them. Photons can interfere with themselves like waves when passing through double slits, creating patterns of light and darkness that demonstrate their wave-like nature. Yet these same photons strike photographic plates as discrete particles, each depositing a specific amount of energy at a particular location. Electrons in atoms occupy orbital shells that represent standing wave patterns around the nucleus, much like the vibrations of a guitar string that can only exist at certain frequencies. These quantum states explain the periodic table structure and the chemical properties that determine how elements combine to form molecules. The wave-like nature of electrons also enables the scanning tunneling microscope, which can image individual atoms by measuring the quantum tunneling current between a sharp tip and a surface. Quantum entanglement creates correlations between particles that Einstein famously called spooky action at a distance. When two particles become entangled, measuring one instantly determines the state of the other, regardless of the distance separating them. This phenomenon does not allow faster-than-light communication, but it does reveal that reality is fundamentally non-local in ways that challenge our intuitive understanding of cause and effect. The many-worlds interpretation of quantum mechanics suggests that every quantum measurement splits the universe into multiple branches, each representing a different possible outcome. In this view, the wave function never collapses. Instead, all possibilities occur simultaneously in parallel realities. While this interpretation remains controversial, it offers a way to preserve the deterministic evolution of quantum systems without invoking the mysterious collapse postulate. Quantum field theory elevates these concepts to cosmic scales, describing particles as excitations in underlying fields that permeate all of space. The electron field exists everywhere in the universe, and what we call an electron is simply a localized ripple in this omnipresent field. Similarly, photons represent excitations of the electromagnetic field, while the recently discovered Higgs boson corresponds to vibrations in the Higgs field that gives other particles their mass. The standard model of particle physics organizes these quantum fields into an elegant mathematical framework that describes three of the four fundamental forces. Quarks and leptons form the matter content of the universe, while gauge bosons mediate the forces between them. The electromagnetic force is carried by photons, the weak force by W and Z bosons, and the strong force by gluons that come in 8 different varieties corresponding to the 8 generators of the SU3 symmetry group. Symmetry breaking plays a crucial role in determining the masses and interactions of fundamental particles. In the early universe, all forces may have been unified at extremely high energies, but as the cosmos cooled, these symmetries spontaneously broke, giving rise to the distinct forces we observe today. The Higgs mechanism represents one such symmetry breaking, where the Higgs field acquired a non-zero vacuum expectation value, endowing W and Z bosons with mass while leaving the photon massless. Grand unified theories attempt to describe the electromagnetic, weak and strong forces as different aspects of a single underlying interaction. These theories predict that protons should eventually decay, though with half-lives so long that detecting this process requires observing enormous numbers of protons for extended periods. Deep underground detectors filled with thousands of tons of pure water watch for the telltale flashes of light that would signal proton decay, though none have been definitively observed. The search for a theory of quantum gravity represents physics' greatest unsolved challenge. General relativity describes gravity as the curvature of spacetime, while quantum mechanics treats other forces as the exchange of virtual particles. Attempts to quantize gravity encounter mathematical difficulties that suggest our current understanding of space and time may be fundamentally incomplete at the smallest scales. String theory proposes that the most fundamental constituents of reality are not point particles, but tiny vibrating loops of energy. Different vibrational modes of these strings correspond to different particles, much like different notes played on a violin string. This theory requires additional spatial dimensions beyond the three we experience, dimensions that may be compactified or curled up so tightly they remain invisible at macroscopic scales. Loop quantum gravity takes a different approach, attempting to quantize spacetime itself by proposing that space and time are granular rather than continuous at the Planck scale. Approximately 10 to the power of negative 35 meters and 10 to the power of negative 43 seconds respectively. At these unimaginably small scales, the smooth geometry of Einstein's relativity gives way to a foam-like structure where the very concepts of space and time lose their classical meanings. The anthropic principle suggests that the fundamental constants of physics are fine-tuned to allow the existence of complex structures like atoms, stars, planets, and ultimately life itself. If the strong nuclear force were slightly weaker, atomic nuclei would not form. If it were slightly stronger, hydrogen would not exist. These apparent coincidences have led some physicists to speculate about the existence of multiple universes with different physical laws, where we naturally find ourselves in one of the rare universes capable of supporting observers. Dark matter and dark energy comprise approximately 95% of the universe's total mass-energy budget, yet their fundamental nature remains mysterious. Dark matter appears to interact gravitationally, but not electromagnetically, forming the invisible scaffolding around which galaxies and galaxy clusters assemble. Dark energy, even more enigmatic, drives the accelerating expansion of the universe through some form of negative pressure that permeates all of space. Cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, explains many observed properties of the cosmos, including its remarkable homogeneity and the tiny fluctuations that eventually grew into galaxies and galaxy clusters. During inflation, quantum fluctuations in the inflaton field were stretched to cosmic scales, creating the seeds of all large-scale structure we observe today. The cosmic microwave background radiation, discovered accidentally in 1965, provides a snapshot of the universe when it was only 380,000 years old and had cooled enough for the first atoms to form. This ancient light carries the imprint of acoustic oscillations in the primordial plasma, sound waves that propagated through the early universe until the moment of recombination froze them in place as temperature variations across the sky. Neutrinos, nearly massless particles that barely interact with ordinary matter, stream through the universe in vast numbers, carrying information about the nuclear processes that created them. Solar neutrinos provide direct evidence of fusion reactions in the sun's core, while supernova neutrinos offer glimpses into the violent deaths of massive stars. The cosmic neutrino background, a relic from the universe's first second, fills all of space but remains undetected due to the extremely low energies of these primordial particles. Gravitational waves, ripples in the fabric of space-time itself, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory. These waves carry information about the most violent events in the universe, including the mergers of black holes and neutron stars. Unlike electromagnetic radiation, gravitational waves pass through matter almost unimpeded, providing a new window into cosmic phenomena that emit little or no light. The hierarchy problem in particle physics asks why gravity is so much weaker than the other fundamental forces. If you could shrink down to the Planck length, gravity would become as strong as the other forces, but at everyday scales, it requires enormous masses, like planets and stars, to produce noticeable effects. This vast disparity in force strengths remains unexplained by current theories and may hint at physics beyond the standard model. Supersymmetry proposes that every known particle has a heavier superpartner with different spin properties. These hypothetical particles could explain dark matter and help solve the hierarchy problem, but none have been detected despite extensive searches at particle accelerators. The absence of supersymmetric particles at accessible energies has led to increasing skepticism about whether this elegant mathematical symmetry actually describes nature. Extra dimensions, if they exist, might be detectable through their gravitational effects at very small scales. Experiments that measure gravitational forces between closely spaced objects search for deviations from Newton's inverse square law that would indicate the presence of additional spatial dimensions. So far, these tests have confirmed Einstein's predictions down to distances of less than a millimeter. The information paradox of black holes poses a fundamental challenge to our understanding of quantum mechanics and general relativity. When matter falls into a black hole, the information it carries appears to be lost forever when the black hole eventually evaporates through Hawking radiation. However, quantum mechanics demands that information be conserved, creating a paradox that may require revolutionary changes to our theories of space, time, and information. As we drift through these deeper currents of the whispering galaxy, we begin to sense that the universe operates according to principles far more subtle and interconnected than our everyday experience suggests. Each quantum interaction, each curved path through space-time, each whisper of ancient light carries within it the story of how reality weaves itself into the magnificent tapestry we call existence. The whispering galaxy holds within its spiraling arms the most exquisite demonstrations of how matter and energy dance together across cosmic time. In the quiet spaces between stars, where temperatures hover just a few degrees above absolute zero, hydrogen atoms drift in their simplest form, each consisting of a single proton embracing a lone electron in quantum mechanical harmony. These atoms, scattered so thinly that each cubic centimeter of space contains barely one, represent the raw material from which all complexity emerges. When these sparse hydrogen clouds encounter the gravitational whispers of passing disturbances, they begin to condense, drawn together by the gentlest of forces. As density increases, so too does temperature, following the inexorable logic of the virial theorem. Gravitational potential energy transforms into kinetic energy, causing the gas to warm as it contracts. This process continues over millions of years, creating ever denser cores within giant molecular clouds that span hundreds of light years across. The critical moment arrives when the core temperature reaches approximately 10 million Kelvin. At this threshold, hydrogen nuclei possess enough thermal energy to overcome their mutual electrostatic repulsion through quantum tunneling, initiating the first tentative fusion reactions. The core ignites, and hydrostatic equilibrium establishes itself as the outward pressure of nuclear fire balances the inward pull of gravity. A star is born, adding its voice to the cosmic chorus that has been singing for nearly 14 billion years. Each stellar voice carries its own unique frequency, determined by the star's mass, composition, and evolutionary stage. Low-mass red dwarfs burn their hydrogen fuel so frugally they could shine for trillions of years, outlasting the current age of the universe by factors of hundreds. These patient stars whisper their nuclear songs in infrared wavelengths, invisible to human eyes but detectable to sensitive instruments that reveal their steady, economical fusion processes. More massive stars sing with greater intensity but briefer duration. A star 10 times more massive than our Sun burns through its nuclear fuel in mere tens of millions of years, its core temperatures and pressures so extreme that it races through successive fusion stages like a cosmic sprint. Hydrogen burns to helium, helium to carbon and oxygen, carbon to neon and magnesium, in an accelerating sequence that culminates in silicon burning to produce iron. The stellar interior develops a layered structure reminiscent of an onion, with each shell burning different elements at progressively higher temperatures. The outermost hydrogen-burning shell operates at 10 million Kelvin, while the silicon-burning core reaches temperatures exceeding 3 billion degrees. This thermal stratification creates complex convection patterns that transport energy outward while mixing newly synthesized elements throughout the stellar envelope. When iron accumulates in the core, the stellar story approaches its dramatic climax. Iron 56 represents the peak of nuclear binding energy, the most stable configuration of protons and neutrons possible. No energy can be extracted by fusing iron into heavier elements, so nuclear burning ceases. Without the outward pressure of fusion energy, gravity wins its ancient battle, and the core collapses in less than a second. The collapse halts when matter reaches nuclear density, roughly 100 trillion times denser than water. At this point, protons and electrons are crushed together to form neutrons, releasing a tremendous flood of neutrinos that carry away most of the gravitational binding energy. The core rebounds from this neutron degenerate state, launching a shockwave that propagates outward through the stellar layers. This shockwave initially stalls when it encounters the dense silicon-burning shell, but the intense neutrino flux, normally so weakly interacting that neutrinos could pass through light years of lead without stopping, becomes so dense that even these ghostly particles deposit sufficient energy to revive the stalled shock. The explosion reaches the stellar surface, ejecting the outer layers at speeds of 10,000 kilometers per second in a core collapse supernova. The explosion synthesizes elements heavier than iron through rapid neutron capture processes that occur in the neutron-rich environment of the expanding shockwave. Gold, platinum, uranium, and other actinides are forged in these cosmic furnaces. They're atomic nuclei built by capturing neutrons faster than they can undergo radioactive decay. The supernova disperses these newly created elements into the interstellar medium, enriching the gas from which future generations of stars and planets will form. The stellar remnant left behind depends on the original star's mass and the details of the explosion. For stars between roughly 8 and 25 solar masses, the core collapse produces a neutron star, an object so dense that atomic nuclei merge into a continuous sea of neutrons. These stellar corpses pack more mass than our Sun into a sphere barely 20 kilometers across, creating surface gravities 300 billion times stronger than Earth's. Neutron stars spin rapidly, sometimes hundreds of times per second, and possess magnetic fields up to 1 trillion times stronger than the strongest magnets created in terrestrial laboratories. When the magnetic axis misaligns with the rotation axis, beams of radiation emerge from the magnetic poles and sweep across space like lighthouse beams. These pulsar signals arrive at Earth with clockwork precision, their pulse periods stable to better than 1 part in 100 million. The most extreme neutron stars, called magnetars, possess magnetic fields so intense they distort the very atoms in their vicinity. In such fields, quantum mechanics predicts that the vacuum itself becomes birefringent, splitting light into orthogonal polarization states that travel at slightly different speeds. The magnetic field energy density exceeds the rest mass energy density of ordinary matter, creating conditions where magnetic forces dominate over all other interactions. For the most massive stellar progenitors, exceeding roughly 25 solar masses, even neutron degeneracy pressure cannot halt the gravitational collapse. The core shrinks beyond the Schwarzschild radius, creating a black hole surrounded by an event horizon from which no information can escape. These cosmic monsters warp space-time so severely that time dilation becomes extreme near their boundaries, creating regions where seconds stretch into hours for distant observers. Black holes are not the cosmic vacuum cleaners of popular imagination, but rather follow the same orbital mechanics as any massive object. Their gravitational influence extends only as far as the original stars, so planets orbiting at safe distances would continue their orbital dance unperturbed. The event horizon represents a point of no return for information and matter, but its location depends solely on the black hole's mass, angular momentum, and electric charge. Rotating black holes, described by the Kerr metric, possess additional complexity in the form of an ergosphere, a region outside the event horizon, where space-time itself is dragged around by the black hole's rotation. Within this oblate region, no observer can remain stationary relative to distant stars. The very fabric of space flows like a river, carrying all matter and radiation along with it. The Penrose process allows energy extraction from rotating black holes through interactions within the ergosphere. An object entering this region can split into two parts, with one falling into the black hole on a trajectory of negative energy as measured from infinity. The escaping fragment carries away more energy than the original object possessed, effectively mining rotational energy from the black hole and slowing its spin. When black holes exist in binary systems, they can accrete matter from companion stars, creating accretion disks where gravitational energy converts to thermal radiation with remarkable efficiency. The conversion of gravitational potential energy to electromagnetic radiation in these systems can exceed 40% efficiency for maximally rotating black holes, compared to less than 1% efficiency for nuclear fusion. This makes accreting black holes among the most luminous objects in the universe. The plasma in accretion disks reaches temperatures of millions to billions of degrees, hot enough to emit X-rays and gamma rays that outshine entire galaxies. Magnetic fields threading through this plasma can channel matter into narrow jets that extend for thousands of light years, accelerating particles to nearly the speed of light and creating some of the most energetic phenomena observed in the cosmos. These astrophysical jets demonstrate the intimate connection between gravity, electromagnetism, and plasma physics on cosmic scales. The magnetic field lines, anchored in the accretion disk and twisted by differential rotation, act like cosmic particle accelerators, converting gravitational binding energy into kinetic energy of relativistic particles. The resulting synchrotron radiation produces the radiolobes and X-ray emissions characteristic of active galactic nuclei. Gravitational waves, ripples in the fabric of spacetime itself, propagate outward from accelerating masses at the speed of light. Binary black hole mergers create the most dramatic gravitational wave events, with two stellar mass black holes spiraling together in their final moments, converting several solar masses worth of energy into pure gravitational radiation in less than a second. These waves carry information about the strong field regime of general relativity, testing Einstein's theory under conditions impossible to reproduce in terrestrial laboratories. The detection of gravitational waves by laser interferometry represents one of the most precise measurements ever achieved in physics. The advanced LIGO detectors can measure changes in arm length smaller than 1/10,000th the width of a proton, using laser light to monitor test masses suspended in ultra-high vacuum chambers. When a gravitational wave passes through the detector, it alternately stretches and compresses space itself, creating minute changes in the interference pattern of laser light that reveal the wave's amplitude and frequency. Neutron star mergers produce gravitational waves at higher frequencies than black hole mergers, accompanied by electromagnetic counterparts that include gamma-ray bursts and optical transients called kilonovae. These events synthesize heavy elements through rapid neutron capture processes, creating conditions even more extreme than those in core collapse supernova. The collision of neutron stars may be the primary source of gold, platinum, and other precious metals in the universe. The electromagnetic spectrum reveals different aspects of these cosmic phenomena across dozens of orders of magnitude in photon energy. Radio observations detect synchrotron emission from relativistic electrons in magnetic fields, while infrared telescopes reveal the thermal emission from dust heated by stellar radiation. Optical astronomy captures the blackbody radiation from stellar photospheres, and ultraviolet observations probe the hot coronae and stellar winds surrounding massive stars. X-ray astronomy opens windows into the most energetic processes in the universe, including accretion onto compact objects, supernova remnants, and the hot intracluster medium in galaxy clusters. Gamma-ray telescopes detect the highest energy photons, produced by cosmic ray interactions, nuclear decay, and matter-antimatter annihilation in extreme astrophysical environments. The cosmic microwave background radiation fills all of space with nearly perfect blackbody radiation at a temperature of 2.725 Kelvin, a relic from the epoch of recombination, when the universe became transparent to photons for the first time. Tiny temperature fluctuations in this ancient light, at the level of parts per million, reveal the density perturbations that eventually grew into galaxies and galaxy clusters through gravitational amplification. These primordial fluctuations originated as quantum mechanical uncertainties during cosmic inflation, a period of exponential expansion in the universe's first fraction of a second. Inflation stretched microscopic quantum fluctuations to cosmic scales, creating the seeds of all large-scale structure observed today. The statistical properties of these fluctuations carry information about the fundamental physics operating during the universe's earliest moments. Dark matter, comprising roughly 27% of the universe's total energy density, reveals its presence through gravitational effects on visible matter and light. Galaxy rotation curves, gravitational lensing, and the large-scale distribution of galaxies all point to the existence of non-baryonic matter that interacts primarily through gravity. Computer simulations of structure formation require dark matter to reproduce the observed cosmic web of filaments and voids that characterizes the universe on the largest scales. Dark energy, even more mysterious than dark matter, drives the accelerating expansion of the universe through some form of negative pressure that counteracts gravitational attraction. This cosmic acceleration was discovered through observations of distant Type Ia supernovae, which appear dimmer than expected in a decelerating universe. The nature of dark energy remains one of the deepest puzzles in modern cosmology, possibly representing a cosmological constant, a slowly evolving scalar field, or a modification of general relativity itself. The interplay between dark matter and dark energy shapes the universe's ultimate fate. If dark energy continues to dominate, the expansion will accelerate indefinitely, eventually separating galaxies beyond the reach of light signals. Stars will exhaust their nuclear fuel, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy where no further work can be extracted from the cosmic energy budget. Yet within this vast cosmic framework, islands of complexity continue to emerge through the self-organization of matter and energy. Planets form from the gravitational collapse of dusty disks around young stars, creating environments where liquid water can exist and chemical evolution can proceed toward increasing complexity. The same fundamental forces that govern stellar evolution and galactic dynamics also enable the delicate chemistry of life itself. The Whispering Galaxy thus reveals itself as a cosmic ecosystem where matter cycles through stars, supernovae, and the interstellar medium in an endless process of death and rebirth. Each generation of stars is born from gas, enriched by the nuclear ashes of its predecessors, gradually increasing the abundance of heavy elements that make rocky planets and biological complexity possible. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all forged in stellar cores and dispersed through space by stellar winds and explosive endings. This cosmic perspective places human existence within a vast web of physical processes spanning from quantum mechanics to general relativity. We are not separate from the universe, but rather a temporary arrangement of atoms that have been cycling through stars and planets for billions of years. Our consciousness represents the universe becoming aware of itself through the intricate neural networks made possible by the same fundamental forces that light the stars and bend the paths of light through curved space-time. As we drift deeper into the whispering galaxy's embrace, we begin to perceive the profound unity underlying apparent diversity. The same physical laws that govern the fusion of hydrogen in stellar cores also determine the chemical bonds that hold our bodies together. The electromagnetic radiation that carries information across cosmic distances also enables the neural impulses that generate our thoughts and dreams. We are woven from starlight and quantum uncertainty, temporary patterns in the eternal dance of matter and energy that began with the Big Bang and continues to unfold across cosmic time. The gentle currents of the whispering galaxy carry us now toward realms where the very small reveals secrets about the very large, where quantum whispers shape cosmic symphonies in ways that would seem impossible to our everyday understanding. Here, in these quiet reaches of space, we encounter phenomena that blur the boundaries between the microscopic and the magnificent, reminding us that the universe operates according to principles far more elegant and interconnected than we might ever have imagined. In the depths of stellar cores, where temperatures soar beyond 10 million degrees and pressures crush matter to densities that dwarf anything found on Earth, quantum mechanics performs its most vital cosmic role. The fusion reactions that power every star depend entirely upon a quantum phenomenon, so delicate it seems almost magical. Protons, those positively charged nuclei of hydrogen atoms, should repel each other with tremendous force according to classical physics. Yet somehow, in the stellar furnace, they overcome this electromagnetic barrier and fuse together, releasing the energy that has illuminated galaxies for billions of years. This miracle occurs through quantum tunneling, a process where particles behave more like probability waves than solid objects. The protons don't possess enough energy to climb over the electromagnetic hill that separates them, but their wave functions extend beyond their classical boundaries, allowing them to slip through the barrier like ghostly phantoms passing through walls. Without this quantum sleight of hand, stars would never ignite, and the universe would remain a cold, dark expanse of unreacted hydrogen. The probability of any single proton tunneling through the electromagnetic barrier is vanishingly small. Yet within the stellar core, trillions upon trillions of attempts occur every second. Even with odds measured in parts per billion, the sheer number of interactions ensures that fusion proceeds at just the right rate to maintain stellar equilibrium for millions or billions of years. It's a cosmic lottery where nearly everyone loses, but the few winners generate enough energy to power entire solar systems. These quantum processes create a delicate balance that determines stellar lifetimes and ultimate fates. The rate of tunneling depends exponentially on temperature, meaning that small changes in core conditions can dramatically alter fusion rates. This sensitivity creates a natural thermostat within stars, where increased fusion rates lead to expansion and cooling, while decreased rates allow gravitational contraction and heating. The star finds its equilibrium through this quantum feedback loop, maintaining steady energy output across geological timescales. As we drift through regions where massive stars have ended their lives in spectacular supernovae, we encounter neutron stars, objects so dense that they represent matter in its most extreme quantum state. Here, electrons and protons have been crushed together by gravity so intense that they merge into neutrons, creating a substance where quantum degeneracy pressure provides the only defense against further collapse. A teaspoon of neutron star material would weigh as much as a mountain, yet this incredible density emerges from purely quantum mechanical principles. The surface of a neutron star presents conditions that challenge our understanding of matter itself. Atomic nuclei, normally separated by vast spaces relative to their size, are pressed so closely together they begin to merge into a continuous nuclear fluid. The distinction between individual atoms disappears, replaced by a sea of neutrons governed by quantum statistics that prevent them from occupying the same quantum state. This Pauli exclusion principle, the same rule that gives ordinary matter its structural integrity, provides the pressure needed to halt gravitational collapse. Deeper within the neutron star, matter enters even more exotic phases that exist nowhere else in the universe. Theoretical models suggest the presence of quark matter, where the fundamental constituents of protons and neutrons become unbound and flow freely in a quantum soup. Some theories predict the formation of hyperon stars, where strange quarks combine with up and down quarks to create particles that exist only in these extreme environments. The precise nature of matter under such conditions remains one of physics' great unsolved mysteries. And so, dear traveller, as we reach the edge of our journey through the whispering galaxy, we find ourselves transformed by the cosmic stories we've shared. From the quantum tunneling that lights the stars to the gravitational waves that ripple through space-time itself, we've witnessed how the universe weaves its grand tapestry from threads of physics both delicate and profound. Thank you for drifting with me through these celestial corridors, where every law of nature becomes a lullaby and every cosmic phenomenon whispers secrets of existence itself. Until we meet again in the starlight, may your dreams be filled with the gentle hum of the cosmos singing you to sleep.